We would like to take you on a short journey around a new skeletal structure, the scale axis transform. The scale axis transform is an extension of the medial axis transform. So let us start by looking at the medial axis first. Given a shape, we call a ball medial if it is contained completely in the shape and it touches the boundary in at least 2 contact points. Of course, there can be many medial balls. The centers of all medial balls form the medial axis. But what happens if our shape boundary is slightly perturbed? The small bumps on the boundary give rise to small medial balls. Therefore, the medial axis of a noisy shape contains unintuitive and often undesired branches. To overcome this unpleasant instability, many methods have been developed. Most approaches compute an importance value for every medial axis point and then filter the medial axis based on these importance values. One such method, the lambda medial axis, has theoretical guarantees for both topological and geometrical stability. We color code with brown the shape reconstructed from the lambda medial axis. For this example, the lambda medial axis starts cutting off the heels of our boot before simplifying all the undesired branches. This happens because the importance values of the medial axis points are computed based on the distance between contact points, and this value does not adapt to the local size of the object. To adapt more to the scale of the shape, we can use angle measures as the importance criteria. Although many topological changes happen during the simplification, this angle filtration gives us a nice result for this shape. But what happens if we allow the shape to be a bit more complicated? At some abstraction level, we might want the simplified skeleton to ignore these holes but keep the other features. The previous methods were not designed for this task. And this is the problem we address with the scale axis transform. To compute skeletal structures which gradually represent only the most important features of the shape, so that we are able to compute such skeletons. To achieve this, we do something else instead of filtering the medial axis. We grow the input shape and consider the medial axis of the grown shape as the simplified skeleton. More precisely, in this example, we would like to eliminate the medial balls corresponding to the less important branch on the left, but keep the whole main branch. So we grow our shape with a simple construction that we call multiplicative scaling. We multiply the radii of all medial balls by a certain simplification factor and consider their union as the grown shape. The balls corresponding to the left branch got covered by larger balls. Therefore they are eliminated. And indeed, the medial axis of the grown shape becomes simpler. With the multiplicative scaling, we eliminated irrelevant features, but we increased the overall size of the shape. To compensate for this, we define the scale axis transform as the set of scaled back medial balls of the grown shape. Now we show that we can use the concept of scale axis transform for computing scalable skeletons in practice. Let us represent a shape as a union of finite number of balls. Using the algorithm of Amenta and Colluri, we can compute the exact medial axis of any union of balls, so here it is for our input. As a second step, we sample the medial axis. Next, we multiply the radii of the corresponding medial balls by our desired simplification factor. We can compute now the medial axis of the union of these grown balls. Since we use a finite sampling of the medial axis, artifacts like these unnatural small hairs might appear. To reduce such effects, we regularize the medial axis by simply applying again our construction, this time for the grown shape with a tiny growth factor. As a final step, we sample the new medial axis and shrink back the corresponding balls. Here is the skeleton and the shape simplification based on the scale axis transform with a simplification factor of 1.2. And this is how it evolves for increasing simplification factors. Notice that by eliminating the regions around the holes, we make in a sense a topological simplification. Additionally, sharp features are preserved as long as their hole supporting region is considered important. Another interesting property is that the scale axis is not constrained to be a subset of the medial axis. Therefore, branches can move or get straightened out as part of the simplification process. As a wrap-up, allow us to show you some more examples, something more than high heels.